Hello class, and welcome to the online lecture for Lab 11 titled Reactance and Impedance. Alright, so we'll start this discussion by looking at the voltage and current time dependence for RC circuits and RL circuits. So if you remember the graphs that we've been looking at over the course of the semester, you might remember for RC circuits, we had a voltage that saturates. So the voltage is proportional to 1 minus e to the negative t over tau. We'll use tau c to indicate that the time constant is the capacitive time constant. So also, the current time dependence for the RC circuit was an exponential decay, so it's proportional to e to the negative t over tau c. So in the RL circuits, we saw sort of the inverse behavior. So we had the current is saturating, so this was I proportional to 1 minus e to the negative t over tau L, so that's an inductive time constant. And it was the voltage across the inductor VL that actually decays over time. So e to the negative t over tau L. So for the capacitor, Vc saturates and I decays as time evolves. And for the inductors, for the RL circuit, VL decays and I saturates. So this just more clearly illustrates the complementary behavior of these components. So what is reactance? So reactance is defined as the resistance to current flow, which is based on the time-dependent current response of both the inductors and the capacitors. So in short, I'll just write here resistance to current flow. So reactance is similar to the concept of resistance in resistors. So let's talk about Ohm's law and then relate it to reactance. So Ohm's law says that the voltage across a component is equal to I times R. So I is the current, I is the resistance. So this is a static case and only concerns the initial time dependence when you flip on the circuit if you're looking at a DC circuit. For AC circuits, you have what's known as AC Ohm's law, or Ohm's law for AC circuits, and it gives somewhat the same relationship. So voltage is proportional to I chi instead of V equals IR, where chi is defined as the reactance. So it has the same form because it's really similar to resistance. Okay, so we have chi L for inductive reactance, or the resistance to current flow produced by an inductor. And then we have chi sub C, which is the capacitive reactance, which is the resistance to current flow from the capacitor. Alright, so next we'll use some math to derive actual functions for chi sub C and chi sub L. And then based on the functions that we find, we will define experiments to confirm the relationship. So, if we apply an AC signal to our circuit, so let's start with the RL circuit. So applying an AC signal to the RL circuit, we have V as a function of time equals V naught sine omega t. Alright, so it's just an oscillating signal with magnitude V0. And we get Vt equals L di dt. If you recall from previous labs, this describes the voltage across the inductor. So It is also given by I0 sine omega t. So we take the time derivative, that spits out an omega term. So it's omega L and changes the cosine to a sine, but we'll just write, actually let's do cosine omega t. Alright, this can also be written as omega L I0 sine omega t plus a phase shift pi over 2. Alright, so this says that the input function, or input and output function, are shifted by a quarter wave. There's a quarter wave lag. Alright, so this describes the time dependence, but when we're just concerned with the amplitude, we can say V0 equals the amplitude here, so that becomes omega L I0. Alright, so this is similar to what we had earlier. So V equals IR, or V equals I chi. So this is I L omega. So this tells us that chi has the form for the inductive case, L omega. Right? So that's our inductive reactance, and this says that chi L is proportional to omega, where omega is 2 pi f. So chi L is proportional to frequency. This is the relationship that you'll be confirming in the experiment. Okay, so now for an RC circuit, we'll now derive the expression for capacitive reactance. So RC, we'll start with the same voltage signal. So V as a function of time is V0 sine omega t. Then we'll say the charge across the capacitor, or through the capacitor as a function of time, is C V as a function of time. Q equals CV, you might remember that from back in the day. So we can write this as C V0 sine omega t from above. And we also know that the current, this is where the time derivatives come in. So the current is the time rate of change of the charge, or this is the time rate of change with charge. So equals d dt of qt. Right, that's all the current is. So we have an expression for q. We just take the time derivative of that. So C and V0 come out because they're not dependent on time. And then we have d dt of sine omega t, which again spits out an omega term, C V0, and then this is changed to cosine, but we can write that as sine omega t plus the quarter phase shift again. So, let's see. This is I equals CV. Okay, so this is I as a function of time. Alright, so that means that I0, or the amplitude, is given by the amplitude on the sine term. So I0 equals omega c V0. And then we can write this in terms of the AC Ohm's law. So V equals IR. So V0 equals I0, where the omega c comes to the other side. And so V equals I chi, this tells us that chi sub c equals 1 over omega c. And again, chi sub c is equal to 1 over 2 pi f c, which tells us that chi c, or the capacitive reactance, is proportional to the inverse of frequency. So that tells us that if frequency increases, the capacitive reactance should go down, which is the opposite of what we found for the inductors. So again, you'll be confirming that inverse relationship experimentally.